In my last lecture, I worked through how we use the recursion relationship for the coefficients in the series solution of the polynomials to get this list of Hermite polynomials. Some other characteristics of the Hermite polynomials are there's a recursion relationship between the polynomials themselves. And so you can find the Hermite polynomial of the index n plus 1 from the polynomial with an index n and the index n minus 1. So instead of having to work out all of those coefficients for every term in the expansion, if you know the first one, like in this case, we knew that H0 we said was going to be 1, and H1 was going to be 2y, then we could find H2 by saying 2y H1 minus 2, in this case, the n would be 2 times well, in this case n is 1, so this is H0. Okay. So that means H2 is 2y times 2y minus 4 times 1, or 4y squared minus 4. And so did that give us the polynomial? So no, I seem to be off by a factor of 2 somewhere. Oh, I'm sorry. Let me go back. Let's try this again. Okay, so get rid of that. Okay, so let's try it again. So in this case, what we're trying to find is H2, and that's when 2 is equal to n plus 1. So n is actually equal to 1. So that means we have 2y H1 minus 2 times 1 times H sub 0. Okay, so now if we put everything together, H2 is equal to 2y, H1 is another 2y, minus 2 times 1. So now we get 4y squared minus 2, which if I go back up to the list we had up here, that's what we get. That's the value we get right here. If we tried H3, in that case now, we have 3 is equal to n plus 1, or n is equal to 2. So therefore, we would have 2y H2 minus 2 times 2 H1. And so H3 is 2y times 4y squared minus 2 minus 4 times 2y. And then that gives us 8y cubed minus 4y minus 8y, or 8y cubed minus 12y. So is that what we get? Yes, 8 cubed minus 12y. So it's a lot easier to use this recursion relation between the different polynomials than it can be to try and come up with all the terms. Yeah. Another recursion relationship is with the derivative, and the derivative of the Hermite polynomial is equal to 2n hn minus 1. So that's another way that you could, in fact, work out what the the other terms of the Hermite polynomial from there. Okay, so the last thing I wanted to work out or talk about is the normalization, because that's critical when we're studying quantum mechanics, because you want to be able to normalize these to a probability of 1. If we integrate over the wave functions over all space, then it should give us a probability of 1. So that means we have to find a normalization for the Hermite polynomials. So remember now, our wave function, I'll call it psi n, as a function of y, is e to the minus y squared over 2 times the Hermite polynomial as an index n. So therefore, we wanted to integrate the probability density over all space. And so we can now write this down as the integral of minus infinity to infinity of e to the minus y squared over 2 hn of y, e to the minus y squared over 2. I'm going to call this hn prime of y dy. And so you notice that the Hermite polynomials are real functions. The e to the minus y squared over 2 is a real function. So taking the complex conjugate of it is just that function. But what I did was I changed the index. So really, if I want to have it in the most general case, I could take the probability density between psi, the index n, and psi with the index n prime. So what I get is this integral of e to the minus y squared. So there's 2 of them, so I get rid of that 1/2. And now I've got the Hermite polynomials, hn, hn prime, integrated over dy. And what I get is the square root of pi 2 to the n factorial times the delta function. The Kronecker delta right here. Okay. So I'm not going to go into how we get this normalization, but in the end, what you would need, you would get this normalization factor out front, which we'll have to incorporate into the wave function, and then now there's a Kronecker delta, which means that these Hermite polynomials are orthogonal to each other, and so it's only when we take a probability density e to the minus y squared hn that we get something that is non-zero. Okay, so that means we can't mix the states. We can't take the we can't look for the inner product of a state n prime and n. That would be 0. So in the end, if we did try to if we did try to take the inner product of 2 different states, or a state and the complex conjugate of a different state, so state n prime and the state n, we would get 0. It's only when we take the it's only when we have the probability density when n is equal to n prime that the Kronecker delta, you remember, is 1. So this Kronecker delta is 1 when n is equal to n prime, and it's 0 when n is not equal to. So that means the Hermite polynomials are orthogonal. Okay, so in the end, I'll go ahead and write down the full wave function now. So the full wave function, so the solution to the quantum mechanical harmonic oscillator is a normalization constant, the mass, omega, the frequency, over pi h bar 2 to the 2n times n factorial squared, all of that to the power of 1/4 e to the minus m omega x squared over 2h bar times the Hermite polynomial of m omega over h bar square root times x. So what I've done is I went back and changed. Do you remember we made the substitution that x is equal to by? So now I've gone back and written my solution, the wave function solution, in terms of x instead of y. So that brings back the m omega terms. And so now we have the portions of it are the Hermite polynomials, this exponential term, exponential decay term, which is proportional to, basically e to the minus x squared, and then we have the normalization right here, the normalization factor in front. And so later on, what we will do is we will work out in class how to get this normalization constant, which I can just call a sub n, which is m omega over pi h bar 2 to the power 2n n factorial squared, all of that to the 1/4 power. So I said we'll work that out later. Not going to do that now. But this is basically it. This is the solution. Now that we have the solution to the wave function, you can now calculate the expectation value for the position, the expectation value of the momentum of your harmonic oscillator. You can calculate the probability of being in a certain state. You now have all the information to tell us the dynamics of what's going on with the harmonic oscillator. So I'm going to stop here.